Okay, so Shabu and Anshu came in and they want me to work this problem. So this is for you. I dedicate this problem to the two of you.
Feel the love.
Yes, feel the love. Okay, so here's number 9 in chapter 11. It's on page 354. And you've got two forces, F1 and F2. These are the forces you're given. And they act along two sides of an equilateral triangle as shown in this figure right here. Point O is the intersection of the altitudes of the triangles, and it's just kind of like right there. Okay, find a third force, F3, to be applied at B along BC that will make the total torque 0 about point O. Okay, let's do that part. Now there is a little what if part which is continued right here. What if, will the total torque change if F3 is applied not at B but at any other point along BC? The answer is no, and I'll tell you why. All right, but let's do this problem. Okay, so start off with, given, find, and solve. So I drew a little picture of it right here. So here's my equilateral triangle. Here's F1 and here's F2, okay? And here's F3 along here. Well, what we want to do is, it's given that this is an equilateral triangle, okay? Now, and that, by arguing geometric symmetry and so on, we can figure out what, these angles are, right? I mean, what's the angle from here to here? It's 60 degrees. So that means we can figure out that this is 30 degrees, right? Because this little dashed line here splits it in half. So that's kind of convenient. But we also know that it's in equilibrium. That means the net torque equals 0. Okay? So if we say, well, if the net torque is equal to 0, that means if I sum all the torques together, whoops, I'm so used to writing force. If I sum all the torques, that will be equal to 0. Okay? So that just means, hey, add up the torque from these, the result from these four forces, and you'll get it. Well, I'm just going to call the distance from the center out here, I'm just going to call this arbitrarily R. We'll call that R. The R is from the center out to where the force is. And because it's an equilateral triangle, R has the same magnitude for all three of the vectors. Now, so this applies a torque, and this applies a torque, and this applies a torque. When you add them up, you get 0. And then that will allow us to solve for F3. Okay? So let's do that. Zoom out a little bit. More room. So what's the torque from F1? Well, remember that the torque for F1 is R, right? Well, we know that torque is equal to R cross F, right? And let's just deal with them. Well, we are going to deal with the direction of it. R cross F, that's R times the force times the sine of the angle between R and F, right? That's the definition of a torque. And what direction is it? Well, you use the right-hand rule. Oh, here's my right hand. Use the right-hand rule to figure out the direction of it. Okay, so let's figure out the torque from due to F1. Well, here's R. It goes right here, and it comes out like this. So what is this angle right here? That would be 30 degrees, right? If this angle is 30, right? I forget what that's called in geometry, but yeah, they're opposite. I can't. I don't know. So I just know that, hey, this angle is equal to this angle. So it's going to be R times F1 times the sine of 30 degrees. Okay, so that's the torque. Now, what direction is it? Well, if I extend R out here And I'm going to use the right-hand rule. So let me put this all the way up here. You go R, cross over to F. My thumb sticks up. So I'll just call that up. You can call it, well, maybe I'll make this the X direction, Y direction, so Z. So Z direction, this is in the, instead of up, I'll be more official. I'll call it the K hat direction. Okay, so the torque due to F1 is in the positive K hat direction. With me?
Yes.
Okay. Now let's figure out for the second force, for F2. So here's R, comes down like this, and it goes like this. So here's the angle, and that's 30 degrees again. And so this is going to be R. It's the same R that was over here in terms of magnitude. And F2 times the sine of 30 degrees, right? It's still 30 degrees. If that's 30 degrees, then that's 30 degrees. And again, if I use the right-hand rule, R cross over to F, it's in the positive K-hat direction. Now, we have F3. So here's R, and R comes all the way like this, right? R. And this is what angle here? It's 150, isn't it? So it's going to be R times F3. Whoops, F3. Times the sine of 150 degrees, right? Well, what's the sine of 150 compared to the sine of 30? No, they're not negative. Think about the unit circle here. Here's 30. Here's 30 degrees. Here's 150. Oh, the y value is both positive. The r is always, so it's the same. So the sine of 150 is equal to the sine of 30. But now let's think about what direction this is in. Here's r. So go, take your right hand and go R and sweep over towards the force. What direction is your thumb pointing? Down. Look, everybody, I know this is kind of hard, and it's really funny. People have actually fallen out of their seat doing tests here. So you take R, and I have to, look at my right hand. This is my right hand. See the, and so, see which side, look at the thumb is right over here. So that must be my right hand. So R, cross over to F, all the way over there. My thumb is down. So this is going to be in the negative K-hat direction. Now it's a good thing that one of these was negative, because these two are positive torques. So this negative torque, you needed a negative torque somewhere to cancel it out. So this is all equal to 0. This torque plus this torque plus this torque equals 0. Okay? And, well, we can cross out the R, right? Because it's just divide both sides by R. And sine 30, well, sine 30 is equal to the sine 150, so that cancels out. And so what I'm left with is F1 plus F2 minus F3. I can divide both sides by also the unit vector by k hat, so they cancel out. But it does. This negative doesn't get canceled out, you see. So equals 0. So that's why F3 is equal to F1 plus F2. And that's the answer that you'll find in the back of the book. Now this is the sledgehammer way to do it, okay? This is like brute force, but it works. But the what if question is very interesting here, and the what if will give you a way to solve this problem much faster. You can almost do it mentally. You don't even need to go through all of this math. It says, will the torque change if F3 is applied not at B, but at any other point along BC? Well, let's take a look at this right here. Well, actually, what I'm going to show is this. I'm going to show you a different kind of problem. Suppose here's my axis of rotation coming straight out, and I've got some r vector like this, and here's where the force is being applied like this. Suppose I have an F like this, so here's r. Actually, hold on. Let me put the F over here so it doesn't interfere with my drawing. So we know that it's r, and we know that the torque, right, is equal to r cross F. You know, r is in the axis of rotation to my application of the force, and then this is my force. Okay, so this is going to make something try to twist. Okay? Now, we say that this is equal to r times F times the sine of the angle theta between r and F, and we'll use the right-hand rule to come up with the direction. I don't really care about this right now. What I do care about is this. Let's extend r like this. Remember, the angle between them is if I took this r vector and picked it up and placed it right here. So here's r again. So in order to do the cross product, you've got to put the two vectors tail to tail. Okay? And it's okay to do that. So here's theta. Well, let me show you something. Here's a little trick. Let's extend F along this line right here. And then what I'm going to do is I'm going to make a right triangle where this distance here is the closest distance to this line that F is parallel and on top of, right here. Right here. Now, if this is theta here, then this is theta, isn't it? Well, here's r. This is a right triangle. This is the perpendicular distance to this line. So this is opposite. So this is equal to r sine theta, isn't it? Well, look what I've got in my torque equation. I've got an r sine theta. R sine theta. So r sine theta is, when you go r sine theta, what you get is the closest perpendicular distance that the force can be if it's along this line. If I just pick up that force and put it right over here, well, now the angle between my new r, my r sine theta, which is just is going to be that's going to get me the torque. Here's my new r. See how r kind of varies? I can make r vary, but it's all r sine theta. It all boils down to this. So this r sine theta is this minimum perpendicular distance. Let's just call it d. Quite often it's called d in textbooks. Or sometimes it's called L for lever arm distance. I don't care. So this is d times F. And notice that d doesn't depend on where the force is, right? I mean, if I put the force here, still that perpendicular distance is still right there. So it doesn't really matter. When I go back to the problem that we're given, it doesn't really matter where F3 is applied along BC. Because let's put F3 right here. The r sine theta will still give me this distance right here. This distance right here, well, here's 30 degrees. Here's F3. Well, here's r. That's the hypotenuse. So this is r sine theta. In fact, that's r sine theta, and this is r sine theta. So it doesn't matter where you apply F3 along this line. the r sine theta will be this amount. It'll be fixed. It won't change. And since the force isn't changing, and this isn't, the r sine theta isn't changing, the amount of torque isn't changing. So it doesn't matter. Does that make sense? Sort of? It takes some thinking about. So, and again, don't be afraid to review this and think about it again. All this stuff takes more than one shot to get.